Hi everyone. In this video, we're going to talk about how you find the x and y intercepts of rational functions, and then we're going to look at how we can put together everything we've been finding and come up with a sketch of the graph of a rational function. All right, so you guys, actually finding the intercepts is no different than how you would find the intercepts of any function, okay? To find a y-intercept, you just plug in 0 for x and solve for y. So if f has a y-intercept, because sometimes a rational function may not cross the y-axis, it occurs at f of 0. So basically, you would just plug in 0 for x. Okay, to find the x-intercepts, okay, and let's go back to finding x-intercepts for any function, you would plug in 0 for y and solve for x. Now, what happens with your rational functions is the x-intercepts occur at the numbers that are zeros of the numerator as long as they are not also zeros of the denominator. Okay, because remember, when you have factors the same top and bottom, which would mean that that number is a 0 of both the numerator and the denominator, that's when we actually have a hole in the graph. Okay, now it's possible that that hole could be on the x-axis, but since the function is undefined for that value of x, we would not call it an x-intercept. Okay, so let's look at our first example. Find the intercepts of r of x. Okay, to find the y-intercept, so I want to show you what happens with the rational functions when you find f of 0. Because honestly, I can actually look at this equation and I can tell you what the y-intercept is without doing any work. Because here's what happens. If I find r of 0, meaning I'm going to plug in 0 for x, you know, what are you going to be left with? Well, I hope you're realizing you're just going to be left with constants. So basically, the y-intercept of the rational function is the ratio of the constant terms. So, you know, any of the numbers that don't have an x with it, because if you plug in 0 for x, that's going to go away anyway, because it's going to end up equaling 0. Okay, so that means, in this case, the y-intercept, and if we write it as an ordered pair, remember, for any point on the y-axis, the x-coordinate is 0. And so the ordered pair for the y-intercept in this case would be 0 and 1/2. Okay, now to find the x-intercepts, we're going to have to factor the numerator and the denominator just so we can determine the zeros. Okay, in order to factor the numerator, I would first start by multiplying the 3 times the 2. And that would give me x squared minus 5x plus 6. And then I would go, okay, well, factors of positive 6 that add to negative 5 would be negative 3, negative 2. But then I have to divide by that 3 that I multiplied by to begin with. 3 divided by 3 is 1. Since I can't divide 2 by 3 evenly, I'm just going to move the 3 in front of the x. So this would be the factors of the numerator. The factors of the denominator, a little bit easier. Factors of positive 4 that add to negative 5 would be negative 1, negative 4. Okay, so notice, see how we have x minus 1 over x minus 1? Go ahead and simplify, because you don't want to include those factors when you're finding the x-intercepts. Because remember, your x-intercepts occur at the numbers that are zeros of the numerator, but are not zeros of the denominator. Okay. Or another way to think of this is you just want to look at the simplified form. Okay, so zeros of the numerator. If I take 3x minus 2 and set it equal to 0, I'm going to get x equals 2/3. So this rational function only has one x-intercept, and that ordered pair would be 2/3, 0. Because the y-coordinate for any point on the x-axis is 0. Okay. Now that you know how to find all the characteristics, so what I'm talking about would be the domain, the discontinuities, the horizontal asymptote, the slant asymptote, and the intercepts. We're now going to put all this information together and sketch the graph of the function. So I wanted to give you some steps that you can follow. The first thing you always want to do is factor the numerator and the denominator. To find the intercepts, which is what we talked about today, the x-intercepts are the zeros of the numerator, okay, as long as it's not also a zero of the denominator. And then the y-intercept comes from the value of the function at x equals 0. That's another way of saying plug in 0 for x. To find the vertical asymptotes, you determine the zeros of the denominator, as long as they're not also zeros of the numerator, because remember, that's when you actually have a hole in the graph. Okay. To find the horizontal asymptote, you want to refer back to those 3 rules. Remember, you compare the degrees, and there's 3 different things that can happen. If the degree of, well, I always kind of like to start with if the degrees are the same, then the horizontal asymptote is the quotient of the leading coefficients, or the ratio of the leading coefficients. If the degree of the denominator is bigger, then the HA is y equals 0. And if the degree of the numerator is bigger, then there is no HA. But remember, you could have a slant asymptote. If the degree of the numerator is exactly 1 more than the degree of the denominator, then you have a slant asymptote. And to find it, you divide. And then once you have all that information, you basically just sketch it out and then plot as many additional points as needed to fill in the rest of the graph. Sometimes you can tell what the graph is going to look like without plotting additional points, but sometimes you have to plot some additional points. Okay, let's look at an example. So, number 1, I'm going to start by factoring. Factors of -6 that add to -1 would be -3, +2. Okay, to factor the denominator, we're going to use difference of squares. So x squared minus 9 factors into x minus 3 times x plus 3. Okay, now you guys, before you cross anything out, because I'm noticing we have x minus 3 over x minus 3, find your domain, okay? Because remember, the domain comes from the zeros of the denominator. And these are the values that x cannot equal. So I know based on the denominator that x cannot equal positive and -3. Now, these are the values of x where the graph has a discontinuity. The discontinuities are the vertical asymptotes and the holes. Okay, so then I would go like this. All right, well, x minus 3 is a factor of the numerator and the denominator. So that tells me that there is a hole in the graph when x equals 3. Because it's at the 0. Okay, meaning you set the factor equal to 0 and solve. Since x plus 3 is still in the denominator, then I know there's a VA at x equals -3. The VA and the hole will always coincide with the domain, okay, because the domain helps you determine the values for which the function is undefined, which creates some sort of a break in the graph. And that break or discontinuity could be a vertical asymptote or a hole. Okay, Now let's go back to excuse me, finding our x-intercept. So the x-intercept comes from the zeros of the numerator. Now, since we crossed out the x minus 3's, the only zero of the numerator that's left is negative 2. So negative 2 comma 0 would be the ordered pair of our x-intercept. Okay, to find the y-intercept in the horizontal asymptotes, we actually want to go back to non-factored form. And we're going to kind of look at it from, like, you're going to look at it at the beginning and at the end, okay? Because your y-intercept is going to be the ratio of the constant terms, negative 6 divided by negative 9, because those are the numbers that are going to be left when you plug in 0 for x. So negative 6 over negative 9 simplifies to positive 2/3. Okay, so the ordered pair for the y-intercept is 0, 2/3. Okay, to find the HA, we're now going to go to the front. Compare the degrees. The degrees are the same. So the HA is the ratio of the leading coefficients. 1 over 1 equals 1. So your HA is y equals 1. Okay, so you guys, let's go ahead and start trying to put this into a sketch of the graph. I like to start with the vertical and horizontal asymptotes. We sketch these lines as dashed lines because they actually are not part of the graph, the actual graph, but the graph approaches the asymptotes. So, you know, it's going to make it a lot easier for us to sketch if we start with the asymptotes. Okay, so our VA is x equals negative 3. So at x equals negative 3, I'm going to put a dashed vertical line. And then our HA is y equals 1. So 1 on the y-axis, I'm going to put a dashed horizontal line. Okay, now I'm going to go to my intercepts. These are actual points on the graph. Okay, so negative 2, 0, I'm going to put a point there. And then 0, 2/3. Okay, between 0 and 1, probably closer to 1. And then there's a hole in the graph when x equals 3. Now, if I wanted to find the actual ordered pair where the hole occurs, I'd have to find f of 3. So I'd have to plug in 3 for x into, excuse me, the simplified version. Because if I don't, I'm going to get 0 to 0, which was about to happen. So I am going to find f of 3, but we need to plug it into the simplified version. So this will give me 5 over 6. Okay, so the ordered pair is 3, 5 over 6. Okay, and that's, you know, pretty close to 1, so I'm just going to put an open circle there. That is an open circle. Now, to sketch the graph of the function, first of all, you guys, don't forget about what your parent function is. Remember, sometimes it looks like this, sometimes it looks like this. So knowing that, like, I can tell that the graph, because it's going to go through the intercepts, okay, and it's going to approach the asymptotes. So I can easily sketch this part of the graph. Now, my guess would be, based on the parent functions, that the other part of the graph is going to look like this. I actually do know that that's true because the only other option with that would be that it looks like this, but we don't have another x-intercept over there. So, and based on knowing what the parent function looks like, you know, I pretty much know that the graph is going to look like this. So it basically looks very similar to the parent function, but there's a hole when x equals 3. All right, let's look at another example because there are some interesting things that can happen with these functions. Okay, so for this one, I can only factor the denominator. Factors of negative 10 that add to negative 3 would be negative 5, positive 2. Okay, to find the domain, I want to look for the zeros of the denominator. So that would be 5 and negative 2. These are the values that x cannot equal. I also know those are the values where there is either a VA or a hole. Now, this is going to be a more complicated graph because we don't have any factors the same top and bottom, so there's no hole in the graph, which means there are two vertical asymptotes, x equals 5 and x equals negative 2. Okay, to find the x-intercept, I now just need to find the zeros of the numerator. The 0 of the numerator is negative 3. Okay, to find the y-intercept, I'm just going to come over here and find the ratio of the constant terms. So that's going to be negative 3 over 10. And then to find the HA, I'm going to compare the degrees. The degree of the denominator is bigger, so my HA is 1 equals 0. All right, you guys, let's just see what happens. So we have two VAs, x equals 5 and x equals negative 2. And then y equals 0 is our HA. Okay, then our x-intercept is negative 3, 0. Let me put that in a different color. Okay, some of you are probably going, wait a minute, something must be wrong. We can't have a point on the horizontal asymptote. Well, we actually can have a point on the horizontal asymptote. So, you guys, I know a lot of times when you first learn about asymptotes, you know, you're taught that it's a line that the graph will approach but never touch. That's not really true. That is true for vertical asymptotes. The graph will never touch across a vertical asymptote, but a graph can cross or touch a horizontal asymptote because remember, the horizontal asymptote really has to do more with end behavior of a function. Okay, so yeah, it is okay to have a point on the horizontal asymptote. Okay, our y-intercept is 0, negative 3/10. So, you know, I'm just going to have to kind of guesstimate there where that point is going to fall. Okay, now, this is an example of a sketch or graph that we're probably going to have to plot some additional points because I'm not really 100% sure what's happening here. So, I can tell you this, in between the vertical asymptotes, it looks like the graph more than likely does something like this. Because we know the graph goes through that point, 0, negative 3/10, and approaches the asymptotes. And there's no x-intercept in there, so I know it doesn't cross or touch the x-axis. So it pretty much would have to have this kind of behavior in between the VAs. Okay, now my options outside of the vertical asymptotes, that's where the sketch is going to look more like the parent function. So I kind of have an overall idea, you know, because like it's going to either look kind of like this or maybe like this. But I'm going to have to plot some additional points, is what I was getting at. So why don't we just plug in negative 4 into our function? And it might be easier just to plug negative 4 into the factor 4. Okay, so we're going to get negative 1 over negative 9 times negative 2. So that'll end up equaling negative 1 over 18. Which is real close to 0. But based on that behavior, guys, I can tell this is what the graph does. It comes down, it crosses the x-axis, but then it's going to kind of come back, and then that's where it's going to then approach the HA. or approach y equals 0. Okay, now let's also plug in a 6, just so I can see what's happening off to the right end of the graph. All right, so I'll have 6 plus 3 over 6 minus 5 times 6 plus 2. All right, so we're going to end up with 9 over 8. 6 minus 5 is 1, so 8 times 1 is 8. Okay, so that's like 1 and 1/8 as a mixed number. So 1 and 1/8 is kind of about right there. But that tells me, because I know the graph goes through that point and then approaches the asymptotes, that it's going to look like this. So that wasn't too bad. We only had to plot 2 additional points. So a little bit more complicated graph this time. And it really is because of the 2 vertical asymptotes. Okay, let's look at this example. Let's start by factoring. Okay, from the denominator, I can just factor out an x. Okay, my domain would be x cannot equal 0 or -3. Those are the zeros of the denominator. I'm also noticing I don't have any factors the same top and bottom, so there's no whole, which means that we have 2 VAs. Okay, the x-intercept or intercepts are zeros of the numerator. So this time we actually have 2 x-intercepts, 3, 0, and -2, 0. Okay, to find the y-intercept, remember how we go back to non-factored form and we find the ratio of the constant terms? Well, the constant of the denominator is 0, and -6 over 0 is undefined. So there's no y-intercept. Okay, and then the HA, the degrees are the same, so we go to the leading coefficients, and we get y equals 1. Okay, now, let's start with sketching the asymptote. So we have x equals 0, which is the y-axis. We have x equals -3. And then we have y equals 1. Okay. Plot the x-intercept. So we have 3, 0, -2, 0. And we don't have a y-intercept. Okay. Now, there are going to be 3 separate parts to this graph, okay, because of the 2 VAs. So I'm going to start with the easier parts. I know, okay, based on the x-intercept 3, 0, which I know the graph is going to go through that point and approach the asymptotes. Like I can easily sketch that part of the graph just using the x-intercept and then approaching the asymptotes. Okay, now on the very outside on the left, because it's really those outer branches of the graph that are going to look like your parent function, pretty much know it's going to look like this. I know that because there's no x-intercept over there. Okay. Now, in between the 2 vertical asymptotes, here's what can happen, you guys. In the previous example, in between the 2 VAs, the graph kind of looks like a parabola. It's not an exact parabola. Okay, and again, we're just sketching here. But a lot of times in between your 2 VAs, because remember, rational functions are the quotient of 2 polynomials. Usually the graph in between the VAs will look either kind of like a quadratic parabola or maybe a cubic polynomial. Okay. This is an example where it's probably only more like a cubic polynomial, but even if you didn't know that, that's okay. We do need to plot an additional point. Okay, so why don't we plug in -1, and we'll see what happens. But just plotting that additional point, I think we'll be able to tell what it's going to look like. And I'm just plugging into factored form. You could also plug into non-factored form. Totally up to you. Okay, I end up getting negative 4 over negative 2, which equals 2. Okay, so negative 1, 2, here's the point. All right, so you guys remember the graph is going to go through these 2 points and approach the asymptote. So it's actually going to look like this. Okay, so I wanted to show you in this example just another possibility of what can happen when you have 2 vertical asymptotes. Okay. Last example. So in this example, instead of a horizontal asymptote, we have a slant asymptote. But again, let's start by factoring. Okay, to find the domain, x cannot equal the zeros of the denominator, so that's positive 3. We don't have any factors the same top and bottom, so there's no hole, which means there's a VA at x equals 3. Okay, there are 2 x-intercepts, zeros of the numerator. So 4, 0, and negative 3, 0. To find the y-intercept, we divide negative 12 by negative 3, and that equals 4. And then if you were to compare the degrees, the degree of the numerator is exactly 1 more than the denominator. So to find our slant asymptote, we're going to do synthetic division. And remember, we're just interested with the quotient. So our slant asymptote is going to be y equals 1x plus 2. Okay, so I'm going to start with the slant asymptote. So if I'm sketching y equals 1x plus 2, okay, that means the y-intercept is 2, and then it has a slope of 1. And then remember, we're just going to put a dashed line through these points. So here's our slant asymptote. Okay, and then our VA is x equals 3. Okay, now let's plot our intercepts. So we have 4, 0, negative 3, 0. We have 0, 4. Okay, so that's all the information that we were given. So, all right, I can somewhat tell what's happening just based on the intercepts and then knowing that the graph is going to approach the asymptotes. So this graph, you guys, is going to look like this. And also like this. So if you can try to envision it, I'd like to, if you replace the horizontal asymptote with a slant asymptote, if you kind of think of, what would look like the parent function, if we took that HA and slanted it, it's going to kind of distort, the way the graph looks. That's how I kind of like to envision it if we change from an HA to an SA. But all right, so you guys will definitely practice this in class some more. As always, thank you for watching and have a good night.